So what we have here is a very classical physics problem where we have a square of charge. At three corners of the square, we have positive charges, and at the fourth corner, we have a negative charge, and the square has sides all of length L. And what we want to do is calculate what is the force that each one of these three positive charges exerts on this negative charge. So we know force is additive, so we need to add up all the different forces that we have. So let's label these charges. Let's label this guy up here charge number 1, charge number 2, charge number 3, and charge number 4. So what we're going to do is find the total force on the fourth charge as to be equal to the force of the first charge on the fourth charge. So I'm going to call that F with subscript 1 and 4. F of 1 on 4. Plus the force of 2 on 4 plus the force of 3 on 4. And I need to add these up like forces, which we know are vectors. Now I need to know what kind of forces I have actually acting here. Since these are charges, it's going to be electrical force, and it's going to be the electrical force between two different charges. So we know that the electrical force between two charges is going to be Coulombs Law. So in general, the force between two charges is K, which is a constant, the Coulomb constant, times charge number 1, charge number 2, all divided by R squared, where R is the separation between the two charges. So this equation right here is going to be our key in writing out what the total force is that's working in this particular problem. So what we want to take note of is how all these forces are acting before we add them together, because these forces are all vectors. So we can only add like directions for vectors. Remember, x direction applies to x direction, y direction applies to y direction. We can't change that. So what I want to do first is write down the vectors and draw in the vectors that give me the directions that these forces are going to go. I have the force of the first charge acting on the fourth charge. So since these charges are oppositely charged, they have an opposite sign, opposite charges attract. So this fourth charge is going to be attracted to the first charge. So that's going to be the vector nature of force 1 on force 4. They're going to be attracted to each other. Then we have force 4, the force between charge number 2 and charge number 4. So where is charge 4 going to go due to the force on charge 2? It's going to be attracted to charge 2. So we're going to have a vector pointing towards charge 2, force of 2 on 4. And then finally the force between 3 and 4, they're going to be attracted to each other, so we get a force of 3 on 4. So we've minimized stuff and kind of moved things up to the corner, and we can see right away that there's two of the forces that are going to be pretty easy to deal with. We can see that F of 1, 4, the force of charge 1 on charge 4, and F sub 3, 4 are acting in only one direction. F1, 4 is in the x direction, and F3, 4 is in the y direction. So they don't have any kind of strange vector components going with them. So let's get those out of the way. F of 1 on 4 is going to be equal to, according to Coulombs Law, K times charge 1, which we are given in this problem, let's say it's Q, times charge 4, which is also Q, all divided by the separation, the radius squared, which is going to be L squared, because L is the length of the side of this square. So this means F14 is K times Q squared over L squared. And you might wonder, why didn't we plug in a negative for this charge? Because this second charge, charge 4, is a negative charge. And when you're doing the Coulomb law force, right now all we've done is found the magnitude of the force. And what this charge does, what this sign of the charge does, this tells you what direction the force is going to go based on how it interacts with the other charge. So we know these two charges are opposite, So force 1, 4 is going to attract the fourth charge to the first charge, which means that we're operating in the negative x direction. And if we remember our unit vectors, the negative x direction is negative I hat. So that's the force of 1 on 4, kq squared over L squared in the negative I hat direction. We can put a little vector symbol over this because we've expressed it as a vector in this form. Now we can do F3 on 4. F of 3 on 4. The other easy force is going to be equal to K times the two charges, Q3, which is just Q, Q4, which is just Q. And remember, we drop the negative because we don't worry about the negative when we're plugging in the charges for the force. And we divide all of that by L squared. And this one is going in the negative J hat direction. And again, we figure that out because the signs of these two charges are opposite, so that means they're attractive. So charge number 4 is going to go down towards charge number 3 because it's going to be attracted to it. So already we've got 2/3 of the answer written down here, F1 on 4 and F3 on 4. Now the hard part comes with figuring out what this guy is, F of 2 on 4, because it's acting at an angle. So what I'm going to do here is I'm going to kind of take this whole triangle system that we're working with up here, this square, and I'm just going to yank out the stuff of interest to us, this F of 2 and 4. So I'm going to redraw it a little bit so that we have our negative charge up here, and then we have our positive charge down here. We know that they're attracted to each other, so I have this F of 2 on 4. And I know that some of this F24 is acting in the x direction, so I'm going to call this F24 in the x direction, and some of it is acting in the y direction, F24 in the y direction. And I can figure out what this angle is. I know that this is 45 degrees because this is a square. So what I can do now is I can figure out what F24 is. F24 is just Coulombs Law again. F24 is equal to K times charge 2, which is Q, times charge 4, all divided by the separation of the two squared. So that's going to be equal to the square root of L squared plus L squared, where that came from the size of this square. So if we go back up to our original picture, we have one side of length L, another side of length L, and the hypotenuse is going to be the diagonal of this square. So I can do Pythagorean Theorem to do L squared plus L squared square root gives me my hypotenuse. A squared plus B squared gives me C squared. So now I know that F of 2 on 4 is equal to K times Q squared all over the square root of 2L squared. And if I know my unit circle, I can very easily figure out what F24x and F24y are. Since this is a 45-degree angle, I know that F24 and x and F24y are going to have the same magnitude. That's going to come from plugging in some trigonometry. So to make this abundantly clear, we'll go ahead and do that. If I want to know what F24x and F24y are in terms of variables that I know, and I know that F24 is this kq squared over the square root of 2L squared, I can use trig to figure this out. I know that the cosine of 45 degrees is equal to the adjacent side, and here we have our triangle, our 45 degrees. My adjacent side is going to be F24x. So this is going to be adjacent F24x over the hypotenuse, which is F24. So shuffling this around, doing the algebra to solve for F24x to get it by itself, I find F24x is equal to F24 times cosine of 45. And if you plug this into your calculator, you'll find the cosine of 45 is about 0.71. So f24x is equal to f24 times 0.7. And then you can plug in for f24. So f24x is equal to 0.7 times k times q squared over the square root of 2l squared. And if I want to write this as a vector, I need to associate a direction with it. All I found now is the magnitude, and the direction is going to come from the picture. Again, the direction comes from looking at the signs of these charges and figuring out what direction this vector arrow is going to go. We can see this vector arrow goes in the negative x direction, so that's going to be in the negative I hat direction. We can do the same process for f24y. We find f24y is going to be equal to 0.7 times k times q squared over the square root of 2l squared. This is what happens when you plug in your trigonometry. If you have questions about that, you need to come to my office or send me an email if you can't figure out how that works. We should be able to do that at this point. But if you can't, let me know. And we want to make this into a vector, so we want to associate our direction with it. And we see from the signs, I know that the negative and positive charges have an attractive force. So our total force is going kind of downwards at this slant. I go in the negative x direction, and I can see I'm also going in the negative y direction. So this is going to be in the negative j hat direction. So that's f24 in the x, and that's f24 in the y. And now, to get my final answer, I go right back to my very initial equation. My total force is the vector sum of all the forces that I have acting. So anything that's going in the x direction, I can add together to give me a total force, let's say, in the x direction. And that's going to be equal to F14. If we remember, F14 was acting entirely in the x direction. So it's going to be k times q squared over L squared in the negative I hat direction. And then I want to add anything else that's going in the x direction, which in this case is going to be F24 in the x direction. So I can add on this 0.7 times k times q squared over the square root of 2l squared, also in the negative I hat direction. And that's my total force on this thing acting in only the x direction. Now I can do the same thing to figure out what's going on in the y direction. In the y direction, I have my f of 3 on 4, which is from the very first part of the problem. So we have our k times q squared over L squared acting in the negative j hat direction. And we're going to add on that 0.7 times k q squared over the square root of 2l squared in the negative j hat direction, which again came from F24 in the y direction. And we can circle that answer as well. And that gives me my y direction force. And this together combines to give me the total sum of the force that I have acting on this negative charge. So this would be a perfectly acceptable answer for the total force acting on this negative charge due to the 3 positive charges.